Michelson interferometer is named after Albert Michelson, who lived between 1852 and 1931. It uses the interference of waves. We know that when waves are in phase with each other, we get constructive interference, and when waves are out of phase with each other, we get destructive interference. This is a setup of a Michelson's interferometer. In this case, a beam of coherent light is incident on a beam splitter. Half of this light is transmitted to mirror 1. The other half is reflected to mirror 2. The beams of light are reflected back by these mirrors, and they combine together and they can be observed on the screen. If the arms are of different lengths, a phase difference between these phase beams can be introduced. So this is what a Michelson's interferometer looks like. You have a source, a beam splitter, 2 images, and then you have a screen. OPD is the distance traveled by the red beam minus the distance traveled by the yellow beam. So if the mirror is moved, the 2 paths, when they are identical, the interference will be constructive. When the moving mirror moves 1/2 of the wavelength, the path difference is 1/2 the wavelength, and interference will be destructive. So one mirror is fixed and the other one can be moved. And from judging what it is doing, we can pretty much figure out whether we're going to get a constructive interference or a destructive interference. Okay, so movable mirror moves back and you get different values of gamma. Now the question is, where are these used? Well, Michelson's interferometer is very, very important for biology of cells, for example. So it's called an interference microscope. What it does is it enhances contrast in the image when viewing the objects that are transparent or nearly transparent. For example, cells in water solutions are nearly impossible to see under ordinary microscopes unless you add some kind of a dye to them. But in this case, you won't have to add a dye to them because the index of refraction is much different of water than it is of cell. And the light transmitted to the cell is now going to be phase shifted when compared to the light transmitted through water. So Michelson's interferometer picks up on that, and the intensity differences are easy to spot. Now let's do an example. A Michelson's interferometer is adjusted so the bright fringe appears on the screen. As one of the mirrors is moved 25.8 micrometers, 92 bright fringes are counted on the screen. What is the wavelength of light used in that interferometer? So, solution. Moving the mirror a distance d introduces a path difference of 2d, right? So we're moving one mirror back, but the total path difference is going to be 2d. The number of bright fringes correspond to the number of wavelengths in the extra path length. So n lambda will be equals to 2d, or lambda equals 2d over n. Knowing the d and the n, we can calculate the lambda to be 0.561 micrometers.